Professor DeAngelis, can you hear? Can you see us? Can you see us?
Yes, I can.
Okay. Okay, so can we start now?
Yeah, anytime.
Okay, so today, our first speaker is Professor DeAngelis from U.S. Geological Survey. So his topic is about the wading bird foraging on wetland landscape. So please, Dan.
Good morning, and thank you. I want to first thank Shigui, Suan, and Jianghong for inviting me. I'm really sorry not to be present physically. Out of an abundance of caution, my agency has limited international travel, so my trip was canceled at the last minute. And I greatly miss not seeing Gail again. We've met at a number of meetings, and we've co-authored 2 papers together. And we had some very nice walks together in Banff, full of beers meetings. So I really miss that interaction. But I do wish Gail a happy birthday. And I'll say, by the way, her talk on augmented phase plane analysis was terrific. I might mention also that for many years, starting in the 1970s, I collaborated with folks at the Ontario Ministry of Natural Resources. So I had quite a few trips to Toronto, which is a great city. And I was really looking forward to another visit, but sorry to miss that opportunity. Okay. First, I should say that the work on this talk was equally shared by all 4 of the authors that I've listed. And the third one, Hyo-Won Lee, is a grad student at Florida International University. He's a very smart guy. I'm going to give a little background first on wading birds in the Everglades landscape to sort of set the context. The left-hand slide shows the southern Florida with the two areas that we've been involved in modeling are Everglades National Park and Big Cypress National Preserve. To the right, you can see this typical landscape in Everglades National Park. It's called a ridge and slough landscape. And the formation, the geologic formation of this landscape has been explained pretty well mathematically by Laurel Larson and Judd Harvey. Their typical landscape is that of these regularly spaced ponds, so especially in Big Cypress National Preserve. I mean, it's a little bit hard to see those, but they're very regularly spaced. And that's been explained also mathematically by Matt Cohen, Daniel Watts, Jim Heffernan, and others. So a lot of the basic underlying structure of the Everglades has been explained very well by mathematical models. But I'm not going to go into those. I'm more interested in how animals adapt to those that geomorphology. The reason we're modeling wading birds in the Everglades is that human disturbances in the 20th century have caused a decline of about 90% of nesting of wading birds in the southern Everglades. There's current restoration efforts to provide more water, and especially the spatial and temporal configuration of the water flows. And it requires guidance on the best way to manage those water flows. I'm going to talk mostly about tactile feeding wading birds as foragers. They're critically dependent on the way water is regulated. Over a breeding season, a wading bird must acquire daily high amount of prey to feed itself and its offspring. And these tactile feeding wading birds, and these include wood storks, white ibises, they need foraging sites with high concentrations of prey, consisting mostly of small fishes, crayfish, and they also need the right water depth range, not too deep. It's got to be somewhere between 0 and about 30 centimeters. Well, the pulsed hydrology of the Everglades creates heterogeneous concentrations of prey across the wetland landscape during the dry season. So these are the necessary conditions for wading birds to breed. And it raises a question then is, how should the wading bird optimally forage in such a landscape? The seasonally pulsed wetland looks a little bit like this. If you look, I don't know if you can see my pointer, but I'm pointing to November. By the end of the rainy season, the water covers much of the landscape, and the fish really propagate under those conditions. As the dry season starts, around December or so, the water becomes constricted and the prey become concentrated. Then it dries out by about the end of April, or a lot of it dries out, not all, and then starts to flood again, the start of the next rainy season. So you can see here, with this increased density, these tactile feeders are finding a lot of prey. So in this kind of a simplistic diagram, you can sort of show the wet season, fish biomass grows, but it's diffuse. It starts drying, and these become condensed. This happens every year, not always in the same way. It can be quite different from year to year. Okay, the places of prey concentration tend to be these calcium solution holes, slough patches along the sloughs, alligator holes, and so forth. Well, there are a lot of different perspectives from which we can look at a wetland ecosystem from the modeling standpoint. And one of these is just to look at the dynamics of changing hydrology, prey, and wading birds in a single pond during the breeding season. And we've done this. Simeon Urich when he was a grad student, and I wrote a paper on this. Another aspect that one can look at is the changing prey distributions across a large section of real ridge and slough landscape, actually taking the actual topography and hydrology. Simeon and I did that. Simeon and others did that back in 2016. If there's time, we might talk about these later, depending on how time goes. So then another aspect is the interaction of many individual wading birds with different personalities over changing landscapes. This is much more ambitious, and that's our current work, primarily going to be using ABMs, agent-based modeling. Finally, a foraging strategy of an individual wading bird on a heterogeneous landscape. And that's what I'm going to talk about today. And that was primarily done by grad student Hyo-Won Lee. Okay, a little bit of foraging theory. There's the prey-centered. It's characterized by Halling type, his functional responses, and that's oriented around the predator's search for and capture and consumption of individual prey items, usually within a relatively homogeneous foraging space. Another approach is that of patch-centered, and that goes back to MacArthur and Pianka, and that's oriented on a foraging space being composed of a heterogeneous array of patches with varying prey availabilities or energetic quality, where ideally the forager selects an itinerary of patches that at least comes close to maximizing intake or minimizing the time spent. So those are two approaches to foraging theory. And we think that wading birds probably have a little bit of both. Certainly prey-centered on a short time scale, that's minutes to hours, in which they may be spending time in a given patch, such as a pond. Patch-centered foraging over a day, where they're going to be visiting a number of ponds or other types of patches. Then a third level is following changing patterns of prey distribution on a landscape over the whole breeding season. So that's where the way water, the topography and the way water levels change through the season are going to dictate what the wading birds are able to obtain by foraging. And that's going to be largely externally driven. That's a little bit harder to put in the form of functional responses. We really need simulation models to follow that. What is known about tactile feeders can be condensed into a simple, one of the main aspects is condensed into the simple statement by Jim Crislin. Wading birds need to sample potential patches to decide where to forage. The energy penalty for wrong choices may be rather severe because the relatively high cost incurred by large birds in moving from place to place. Thus, there's probably considerable pressure for wading birds to sample foraging patches efficiently. So we see these birds as primarily sampling. They do a lot of sampling, moving from place to place, probably trying to figure out, or probably trying to locate those patches that are best, in which they should probably stay for a longer period of time. So this is just a little schematic of, in this case, that's a wood stork moving from patch to patch. That's just an idealized sort of thing. Our present objectives are to develop an analytic approach to estimate prey intake for a single wading bird foraging on a landscape over a day. We're going to use analytic expressions to describe feasible distributions of prey densities in patches across the landscape and calculate the expected prey intake for different prey density distributions and different foraging strategies. So we think this can be done analytically. It's really idealized, but it's just for the purposes of getting a handle on what these wading birds may do. So I'll go into the methods. So we're going to assume here two possible strategies for sampling. And a major assumption is that the wading birds don't have a priori knowledge of prey densities when they start foraging during a day. That's probably not a correct assumption, but it simplifies things for us. It makes what we're doing, I think, more interesting. So the two strategies we're going to talk about, and one is prey density threshold based. And we're going to assume that the wading bird samples prey patches, expecting to reach a predetermined prey density. So they already have in mind that they're going to wait until they get to a patch that has some prey density that they are happy with. They estimate the prey densities rapidly at each patch and move to the next patch unless it has an acceptable. They keep moving to patches until they find one with acceptable density. How do they actually estimate these densities? We don't talk about that. We're not sure how they do it. My guess is we're going to look into that later. They probably use some sort of Bayesian, innate Bayesian statistics, figuring out whether they've really they made a correct estimate of prey density. But we're not going to talk about that. The other strategy is memory-based, and that is they sample a fixed number of patches, then use memory to return to the highest quality patch. So these are two hypothetical strategies. We don't know what they really use. Unfortunately, it's been difficult to follow individual wading birds around, moving from patch to patch during a day. That would be very nice for empirical people to do, but there's really very little evidence of what they're actually doing. There's a lot of information on the wading birds flying from their nesting area to areas where they can forage, but the within day movement from site to site, patch to patch, doesn't seem to be very well known. So we're just hypothesizing these two possibilities. Well, we have a lot of simplifying assumptions. To make this modeling easy, we're assuming no interactions. That is, no competition, no information transfer. That's such as using cues with other wading birds, no risk of predation. And as I said before, no a priori knowledge of prey availability. We're assuming the wading bird feeds in every patch that it visits. So if it visits a patch, even if it's just sampling it, it's going to be eating prey while it's there, as long as it's there. There's a time limit. We're assuming team minutes, maybe 600 or so minutes for foraging during a day. We're assuming there's a mean time we're calling T sub min needed to sample a patch to determine prey density. These are all assumptions. Mean time to travel from one foraging patch to the next, we're calling that T sub transition. And we're assuming that both T min and T transition contribute to the total time. So the total time that the wading bird has is all the time it spends either sampling or transitioning, or if it does find a site that it likes, that time that it spends there. Also making the assumption that prey density within a given foraging site is not depleted while the forager is present in the patch. Well, that sounds like a severe assumption, but actually it's not. Prey density may actually be increasing because of evaporation causes the pond to be shrinking during a day. So we can't say one way or the other in the course of a single day whether prey density is increasing or decreasing, even if it's being exploited by wading birds. We're also assuming that the forager is an energy maximizer, not a time minimizer. So all of these assumptions can be relaxed, but to make things simple, we're going to make these assumptions here. The analytic expressions are assumed for prey density distributions in patches across the landscape. We're going to make the analytic assumption that the prey density, this is called prey dense, is the prey density in a patch. And it's convenient to describe these by gamma distributions. And we'll just use gamma distributions with values of nu and alpha with just values of nu equals 1 or 2 and a variety of values of alpha. So we can get these curves that either linearly, that are either exponentially decreasing curves or unimodal curves, depending on what nu is. Okay, the first foraging strategy 1, that is sampling until a prey threshold is reached. This diagram shows that. So the probability of reaching a patch above the prey density threshold can be given by, we're going to call that P, which is 1 minus the integral from over the prey density distribution, f of prey dense, which is quite general at this point, from 0 to prey threshold, So it's 1 minus this integral. So prey threshold is the prey density that the prey that the wading bird has selected, that is going to wait until it reaches that density. So one could look at the probabilities of prey thresholds being reached at after various numbers of patches are visited. And we illustrate this by reaching on that prey prey threshold on the first, second, third, or nth, or maybe it will never find it. So we keep track of the transition times that are required that add up to the time it's spending, the time that's spent in low quality patches before it finds the patch that it really likes, and then the rest of the time, given that this is assumed to be a energy maximizer, is the total time available minus all of the times it's spent either searching for prey or sampling. Okay, then we can calculate the average time needed to find a patch above threshold density. And I won't go through this, but it's just the average time to find a patch. It's the summation over time costs. And this is under the assumption that it has found a prey, so it has to be divided by the so this is conditional on it having found a patch above its threshold. And it's just a summation over time costs that occur if the wading bird has found a patch on the at the nth trial times its chance, the time cost times the chance of finding it on the lowercase nth trial. And we get an expression like this, which involves transition time, the sampling time, P, Q, and N. Capital N is the maximum number of patches that can be visited in a day, which is capital T over T min over plus T transition. So this is the basic formula we're going for using in the patch, the density threshold case. Now, so this is the average time taken. The mean expected daily intake has the following form, in which now I'm introducing a new CONS, the rate at which prey are consumed within a patch, that is grams per minute per unit density, where the first part of this, the upper line here, represents the prey intake that it gets from all of those patches that are below its threshold density. So it's visited a number of patches, and but it's obtained energy in those patches, and that's given by this expression. The bottom expression is the energy that it obtains once it has given that it has reached a patch with above its threshold. It's the energy that it intakes at that point from that patch. Okay, we can then, given our general formula, we can input gamma, our assumed gamma distributions. If the gamma prey density distribution is with nu equal 1, we get the following. And I'm not going to go through these. All of these things are demonstrated in our paper by Lee et al. In the appendix. When nu is equal to 2, we get the following expression. So in this case, we just have the only parameter from the gamma distribution are the alphas. And these are our values of prey threshold, and these are values of both P and Q, which depend on the distribution and what prey threshold the wading bird has chosen. Okay, so that's basically what the formulas we get for foraging strategy 1. For foraging strategy 2, which is the sampling of patches combined with memory within a day. They sample a fixed number of patches and then they return to the one with highest prey density. Royston calculated the expected value given a sample of n objects. An expression for the rth largest value within that sample is given from a distribution. And that's given by this formula, which depends on the number of patches sampled, or in this case, our case, patches sampled, the rth highest, and the probability distribution, and the cumulative probability distribution of that of f of x. We can set r equal to 1 because we're only interested in the best patch found. In this case, the expected sample maximum E of 1n is given by this formula below, which we call E sub max n. And this can be evaluated numerically. We haven't tried to evaluate this algebraically, but it can be evaluated easily numerically. So given the energy in the content in the best, we can, in the best patch, we can calculate the expected energy intake over the course of a day using this approach. So we know for the total sampling for n patches, the total time spent in the sampling is n times t sub min plus t sub transition. That is the total time it takes moving from patch to patch, plus that sampling within that patch. And then returning to the best patch also takes some time, which we can just simply assume is the same as the mean transition time. Then there's time after you've sampled those n patches in this amount of time. There's time left over from the total time in that day, capital T, that is the wading bird that can then go back to that best patch and use that time to forage within that patch. So then the expected time, the expected prey intake from that patch is just that time that it can spend there, times CONS, which is the amount of prey that it's harvested, it is able to consume per minute, times Emax, the best, that's the prey density in the best patch. We can also find the average prey quality below the patch that's best, and that's given by this formula. You can go back to Royston to find this. This is the mean of all of those. This is the average of all of those patches that it sampled but weren't the best. So the expected mean from the rest of the patches visited is n times T-min, that's the number of patches visited, times the time that they had to spend there, times CONS to give the expected time from the rest of the patches. Then the expected daily food intake for the whole day involving returning to the best patch is given by the formula below. Okay, so results. Just a We had to use parameters in this model. This is the set of parameters that we've used. And except for a few of these, we make no claims that these are related to reality. We're just assuming that the time estimate needed to estimate prey density is 20 minutes, the time to travel between patches, 20 minutes, time available, 600 minutes, and probably the rate at which prey encountered or consumed, that's probably a little bit that's been estimated. We assume that they can only at most get to 15 patches. Also, the prey needed, we also are using, we're not using in our model, but it's also nice to know the prey needed by, say, the average white ibis is about 600 grams of wet weight per day it needs to ingest from prey. Prey threshold, that we're allowing that to vary, and our prey, our gamma parameters, nu and alpha. Okay, foraging strategy 1, that is sampling until prey strategy is reached. First of all, we can calculate the time and probability to reach prey threshold in strategy 1, the prey density threshold strategy, and the average time to find for this particular nu equal 1, alpha equals 0.16, just to find to arrive at prey density thresholds, prey densities at these particular prey densities take a certain amount of time in minutes, estimated from the model. But the probability of actually reaching these prey densities goes down pretty fast. So it's fairly high for fairly low prey densities, and it starts to go down pretty fast. So, for example, if the wading bird has a prey threshold density of about 20, it has a 50% chance of reaching it, and could probably reach that in about 250 minutes. So that's our first theoretical result. Next, using the formula for predicted prey intake at different prey spatial distributions as a function of prey threshold, we get the following curves. This is prey intake in grams wet weight over the course of the day. And this is the assumed prey threshold density. So if this is what the wading bird is waiting to find, and this is, given what that threshold is, this is the expected intake. And this is done for various values of the gamma distribution, alpha and nu. And I'll just point out one thing. This top curve, first of all, so I mentioned this horizontal line is the mean needed daily prey intake by the white ibis, about 600 grams wet weight. So all of these strategies, at least over for all of these gamma distributions, a certain range of strategies at least works for getting more than that intake. In particular, for a landscape with alpha equals 0.16, nu equal 1, they get a huge amount of energy at their peak strategy, which is assuming about a prey threshold density strategy of about 10 grams wet weight. So they're waiting around to get to that prey density before staying in that patch. One interesting thing is that, so this is for alpha equals 0.16, this is for nu equal 1. this is for alpha equal 0.32, nu equal 2, and those actually have the same prey distribution over the total prey over the whole landscape. They're just distributed in different ways. This is distributed according to a negative exponential. This one's according to a unimodal peak. It's very interesting that this first curve with the negative density distribution, even though the same total prey average prey density across the landscape is the same, gets a much higher prey intake. So the two have the prey distributions have the same mean prey density across the landscape, but the wading bird does much better in the first case. We can also look at the effect of both travel time between patches and the time that it is required for sampling. In the curves that I showed in this case, we're assuming that both of those times take 20 minutes. It takes 20 minutes to sample a patch, takes 20 minutes to move between one patch and another. Those are increased in the model, each to 40. This very nice high curve is depressed to a much lower curve. So obviously, this is sort of an obvious result that that travel and sampling times, the larger they are, the less the less is likely to be the expected prey intake. Okay, so those are some very quick results for foraging strategy 2, that is sampling patches combined with memory within a day. First of all, we can find the expected highest density patch visited for strategy 2 as a function of number of patches visited. And the solid curve gives what is found from Royston's formula. That is the sample size, that's the number of patches visited. The solid curve gives the expected sample maximum. That is the maximum, the maximum in this case prey density that the wading bird is likely to find, patch with the highest density. This dashed curve is, you can do simulations also. You can actually simulate this. And so we did this and looking at 200 replicates, we can reconstruct this curve approximately. So this prey density distribution is for nu equal 1, alpha equal 0.16. So that's the expected highest patch density. From that, we can calculate the expected prey intake from the formulas I gave a little bit earlier. And this is the expected prey intake for strategy 2 with nu equal 1, alpha equals 1.6. And you can see the peak here. This is the prey intake. It's the maximum is above, it's close to 700 grams wet weight. And it comes from visiting about 6 patches, seems to give the maximum. That's, of course, for this particular assumption or set of assumptions we've used. Another thing we can find is, again, as we did in the strategy 1, if travel and sampling times are doubled, the prey intake really goes down. So again, these theoretical curves are shown as solid, and we've done simulations also that show that that match the theoretical curves. And we can again compare the different prey the different expected prey intake for different prey distributions as governed by the gamma distributions. And note that we've paired this curve and this curve. The top one is nu equal 1, alpha equals 0.16. The other is nu equal 2, alpha equals 0.32. Both give the same mean prey distribution across the landscape. But again, as in our strategy 1, the wading bird is going to get a lot more prey, given that if the prey are distributed across the landscape as a negative exponential, it is for a nu equal 1. And these are just curves for the other values of alpha and gamma. Okay, well, some conclusions. Both the prey threshold strategy and the memory of highest prey density patch lead to peaks in prey intake. So there do seem to be optimal strategies there, and it would be nice if we had some data that showed that wading bird use those strategies, but we don't. In the prey threshold strategy, it's most effective to have a prey density threshold. It's somewhat higher than the mean prey density on the landscape, but not too high. Well, we didn't really show that here, but it can be shown that that's seemed to be the case. The forager that used the memory strategy seems successful by sampling a relatively few, lower number of patches than I would have guessed. In this case, at least for the strategies for the distributions we've used, about 5 or so patches before returning to the best of those it has visited. The time needed to travel between patches and the time needed to assess prey density in a given patch can obviously affect the optimal strategy. Okay, next steps. So that's what we did here, but we plan to extend this. And as I kind of mentioned earlier, our current work is looking at a real managed landscape. And to do this, we're going to represent the landscape by a realistic spatial arrangement of a finite number of patches. It can be sloughs, ponds, etc. Simulate additional foraging strategy, such as using visual cues from other wading birds, and simulating as many individuals simultaneously to assess the effects of interactions. And we'd like to be able to predict distributions of wading birds across a landscape. They may not all cluster in the same patches. They probably distribute to some extent. And it may depend on the individual personalities of the wading birds as to whether they're very, very good cue followers or like to go off on their own. And compare strategies for maximizing prey intake with minimizing time spent foraging. So they might, I think that our results for maximizing prey intake probably give hints as to what the wading birds should be doing for minimizing time spent foraging, but we're not sure. They might be a little bit different. Okay, so and we know that these wading birds forage in large flocks. So obviously, simulating one individual wading bird is not very realistic, and but I think it's a good starting point to at least get a sort of a feeling for what they may do. But wading birds follow cues, and so we get big congregations of this sort. Okay. This work was supported by U.S. Geological Survey's Greater Everglades Priority Ecosystem Research Program. And so thank you very much. I think I came in under my time. If you want to see more things, I can discuss some more results, but I think this might be a reasonable time to stop.